NCl3. Ooh. On the back of your packet, because this isn't an actual practice problem that I typed in, it's just one from the mind and the internet. Okay, so NCl3. First step is we have to know how many electrons, how many valence electrons we're dealing with. So nitrogen has how many? 5, because it's in group 15. Plus, each chlorine is 7 times 3 is 21, so a total of 26 valence electrons. All right, so draw everything out. So just making sure you're back here. Hey, keep your head up. Gotta pay attention. Right, this is just an example. All right, so which one's going to go in the center? In. And what's going to spread out around it? The Cl's. Well, if they were to evenly spread out, it would look kind of like this. Cl's. All right, so how many electrons did we just use up by drawing those 3 bonds? 6. 2, 3. So, yep, 3 pairs, 6, 20. Guys, please don't have your heads down on your desk. All right. Now we go to what first to put on electrons? The outside. Chlorine. Each of our chlorines need how many more each? 6 to make 8. So how many did we just use up? 18. So we need 2 more. Our leftovers go where? On the inside, on the center atom. Again, if I was to redraw this whole thing, they would all want to spread out like this, and then the lone pair would be over there, right? Because these are all electrons, but I'm not going to redraw it. Okay, so then that we took care of those 2, now we need to make sure that these are all 0 because NCl3 is neutral. It doesn't have a charge like a polyatomic ion. So we just have how many different types of atoms? 2. We have nitrogen and chlorine, and the nitrogen or all the chlorine look the same. Sometimes we'll run into it where one chlorine might look different than the other, so we would have to check both. But all these chlorines just have 1 bond and 3 pairs. And what does nitrogen have?
3 bonds.
1 pair. Sweet. All right. Formula. How many valence electrons does nitrogen have? 5. Minus how many bonds? How many loners? 2. Equals? Sweet. Chlorine should have 7 minus how many pairs? How many lones? For a total of 7. Got you again. It happened again. You said 7. It's okay. Didn't Luz do it yesterday, last class too? Like, what is 3 minus 3? 3. No, it's all good. All right, so do we need to adjust anything? No? Okay. Now, yesterday the question was asked by, or not yesterday, the day before, what would we do if they weren't 0? That's a great question. We're going to learn how to do that. What we'll have to do is start doing some double bonds. So, you see how these are singly bonded together? Yeah? Well, sometimes things exist where they share 2 pairs of electrons between them. So 2 bonds, double bond. Some things even have a triple bond, but we won't be messing with those. Last thing, what is the geometry of this? Trigonal. Trigonal what? There's 2 different trigonals. Pyramidal, yeah, it's like pyramid. Trigonal, pyramidal. All all right, because it has 3 bonds and 1 lone pair. And if you can see how it's drawn, you see how they're all spread out? Like the lone pair is like the top of the pyramid, and then the 3 are like a tripod on the bottom. That's what it would actually look like if we could draw it 3D. Oh, okay. All right. All right, guys. So now let's go to number 5 on your practice. We did water last class, correct? Yeah. Water, the bent molecule. All right. So let's broaden our horizons with some double bonds. We got CO2. I will tell you that whenever you find double bonds, oxygen tends to like oxygen or double bonds. It doesn't always form double bonds, like in water. It doesn't form double bonds, but oxygen tends to like the double bonds. All right. So if you see oxygen, you might be suspicious of it. Are you going to be double bonded? What is going to be our center atom here? C. All right, so then we put the other 2, we can just put them in a straight line off of it. How many valence electrons are we going to need for CO2? 16. Has 4 plus 6 times 2 is 12. So 16 valence electrons. So then, how many did we just draw? 4? So that takes care of 12. So how many are we going to have now? 6 where? On each of the oxygens, the outside. All right, so that helped us use up the remaining of our 12, so now we have 0. But what looks a little off about carbon? It doesn't have 8, it only has 2. Center bonds do not like to have less than 8, okay? So something's going to be off here, but let's check our formal charges to make sure. Oxygen and carbon. Oxygen has 1 bond and 3 pairs. Carbon has just 2 bonds. I need to stop erasing this. All right, so valence electrons for oxygen? 6 minus? How many bonds for oxygen? 1. Yes, 6 lone pairs. 6 minus 7 is -1. Oh, man, we're seeing something different. What's going on? Carbon should have 4. How many bonds do we have? Plus how many lone pair? 0. 4 minus 2 is? It's 2, and so it'd be considered positive 2 since it's positive. We have charges. Oh, no. All right, so here's the dealio. We need neutral. We need neutral. We don't want those charges. So we're going to switch stuff up by adding, what did I say? Double bonds. Now, we already used up the max electrons that we could, so we can't add any more electrons on. We can just kind of shift them around. So what happens is the oxygens, they start to get kind of friendly. They're like, hey, we'll share with you. We'll try to make this thing right. So I can really take off any of these that I would want to, but I tend to swipe this one, make it a double bond. Huh, what? So I just move it. Instead of it being outside and alone, it decides to share with carbon. All right, oxygen still has 8 around it, but now we're starting to get it so that carbon can have more than 4 electrons around it. Now how many does it have? It has 3 bonds, so how many electrons? Okay, so we're almost to an octet. So what do you think we might want to do to this oxygen as well? Yep, take a lone pair and make it double bonded. Again, I just take the outside one because if not, the oxygen looks a little lopsided. I like to have them the same on both sides. All right, so check your formal charges of the oxygen and carbon again, guys. they're working on something. All right. You guys should have found the formal charges. And hopefully they're beautiful. All right, so oxygen, again, 6, we need 6. But how many bonds do we have now? 2. Plus how many loners? 4. 6 minus 6 is 0. Sweet. What? That's slightly satisfying. You gotta admit that's kind of cool. And then carbon, we need 4 of them. How many bonds? 4 plus how many lone? 0. So, 0. So is this a happy structure? Yes. Heck yes it is. Go happy structure. This is our geometry. Now, when we look to see what the geometry is called on the front, all right, we don't count these 2 bonds as like having 4 things off of it, because in reality, how many atoms are attached to the carbon? Only 2 things. There's 2 oxygens. So, which structure? Yes. If you look at the very top, straight line, 180 degrees between the bonds is linear, right? We just count this as having 1 and 2 things attached to the center, even though they're double bonded together. Do you think double bonds are stronger or weaker than single bonds? Stronger. They are stronger. Do you think a triple bond is the strongest or the weakest? Strongest. Right? They're extra strong. So this is linear, and that was its geometry. Double bond's not too bad, right? It just means having to do more formal charge, more like check and change, check and change. It's a puzzle that must be solved. Ah, dang it. I was
say something, but I thought you had it.
I know. I thought I would remember too. It's okay. I can write it again. Next time, if I do it right before, Brian, you have to go, no, don't erase it.
Very loud.
Very loud. All right, do SF4. You guys can do that one by yourself. I'm sure of it. Practice. You can leave it on. And I'll do interpretive dance moves while we rate. Just kidding. Whatever. I'm over it. I'll give you a hint that it's a lot like one of the bell works that we did. Calculate those valence electrons fast. San Francisco 49ers, I don't know. Kind of? No? I didn't think so. Just roll with this. It's kind of crazy at first. Just roll. Do you know what I'm talking about when we find the valence electrons? Do you know like the pattern?
Yeah.
Okay. Okay, cool. Yes, you may. Stay hydrated.
That's why I just leave thirsty. Must be thirsty, my friends.
Nope. Not that reference. It's unfortunately not the best school appropriate reference. Guys, focus on what you're supposed to be doing, not side conversations. I can hear what you're talking about. What? Not right now. Okay, so we can go through this one fairly fast. Pretty confident that you guys can do this one well. How many valence electrons for SF4? 34. Because 6 plus 7 times 4 is 28. What? Not exactly. If you look on the back, it's SBr form. So very similar, just a different halogen. You can see clear. So S was in the middle. You should have bonded all of them. Taking away how many from our count? 8. 8. How many around each fluorine to give them an octet? My college professors would get tired of making dots, and they had like chalkboards, so they really had to like draw a circle, and so they would just like they would do like that to each side. Like, come on, if I have to draw the dots, so do you. I know, I don't have a chalkboard, mine's easier. Okay, so how many electrons did we just use? 24. So then our last two go where? On S, and again, in reality, they will all want to spread out around the S because they're repelling each other. They're all negative electrons. All right, so when you check their formal charges, 1, 2, 3, 4 dots. 6 minus how many bonds? Plus how many loners? Equals, sweet. 7 minus how many bonds? Plus how many loners? Oh. Equals, across. Whoa. 7 minus 7? 7. 0. I didn't get anyone. Okay, cool. So is that our structure?
I think it's actually 7.
No. 7 minus 7, 0. So what shape is this in with 3 bonds and 1 lone pair? Seesaw. You kind of see like the lone pair sticking up, and then it's like
Basically, sulfur with anything in the 7th group is going to be the same exact thing, but with different letters.
Nice observation. Yes, because if they're in the same group, they have the same amount of what? Valence electrons. Ah, cool. We're establishing patterns and we're understanding. No. I'm telling you that I probably didn't give you all of the same kind. I probably tried to give you a bunch of each kind. Okay, so now we start into the fun part. Number 7 is sulfate. SO4 negative 2. Whew.
What does the negative 2 mean?
Well, that is a great question. So now that means when we have all of our formal charges, they all need to add up to what do you think? Negative 2. So we might have formal charges of negative 1 and negative 1 and 0 and negative 2 and plus 2. All together, they have to add up to negative 2. That obviously doesn't. That was just... Oh, actually it does. Ha! Ha! Cool. And there are multiple ways to draw this, but there's one way that's usually the best. So I'm going to show you the initial way to draw it and then the best structure. So SO4 negative 2, we need to know something about electrons and what happens when they're lost or gained. So if I lose electrons, that means the substance becomes positively charged. I know, it's against what you would think, like, doesn't lose usually mean negative? But in this case, lose means the substance would have a positive charge. And if we gain electrons, what charge would we have? Negative charge. Now, this might seem weird and backwards, but what charge do electrons have? What? Negative. So if I gain more negatives, more electrons, I'm going to have a negative charge. So what's happened to SO4 negative 2? What's happened? It's gained how many? 2 electrons. Cool. All right, so we have to factor that in when we're counting up our valence electrons. So how many electrons will sulfur have? 6. Plus how many total for oxygen? 6 times 4 is 24. And then we gained how many? 2. Sweet. Whoa. 32, you see? It's weird, right? Trippy. So we need 32 valence electrons on our SO4 structure. So what's in the middle? S. And what is bonded all the way around it? O. How many of them? 4. O. Remember I told you that oxygen in a lot of these. I liked that. That was nice. Ooh, we should form a chemistry band. Yeah, wouldn't that be a hit in Nerd Street? Yeah, I know. All right, how many can we subtract from our 32? 8. So how many does that leave us with needing to place? 24. Remember I told you that oxygens typically in Lewis structures, they form some double bonds. Not every time, but always be on the lookout for them. All right, so where are we going to put these 24? On the O's. How many do O's need? How many on each of them, though? 6 to make their happy octets. Whew. They gone. That's right. We used how many? 24. Okay, so we cannot add, we cannot take away electrons. The only way we would be able to adjust is by forming double or triple bonds. And I'll just tell you that we're not going to be working with triple bonds this year. Okay, so let's check our formal charges. So SO. Sulfur has 4 bonds. Oxygen has 1 bond. And 6 loners. I am writing it one more time. Bonds plus lone. Okay, so valence electrons for sulfur? 6. Minus how many bonds?
4.
Plus 0 equals 2. Okay, positive 2, thinking in positives and negative 2s. All right, so we need ultimately all these to add up to our negative 2. And oxygen, 6 valence, 1 bond, and how many lone? 6. So, yes, negative 1. Okay. So, they have to add up to negative 2 together, and one more goal is that the best Lewis structure will have the least amount of charges on it. Like if it can only have 1 or 2 atoms with a charge, it likes that. If every single atom has a charge, it's not as ideal of a structure. And I'll show you what I mean by that. So my sulfur is a positive 2 right now. And then what are all my oxygens? Negative 1. Negative 1, negative 1, negative 1, negative. Okay, so let's add all these charges up and first see, do they add up to negative 2? So negative 4, 1, 2, 3, 4, plus how many? 2. So what's our overall charge? Negative 2. Okay, good. We have an overall charge of negative 2. But every single atom has a charge on it. Right? So this is one way to draw this molecule, but there is a better way to draw it, where there's less charges. And if you take chemistry in college, which I suggest you do, you'll find that sulfate actually has like 6 different ways to draw it. Right? But there's, again, one most ideal way. Gets crazy. I remember my professor was like, pick 10 polyatomic ions and draw the structures. And I was like, great, I could do that. But then I picked sulfate and it had like 6 alternate ways. And I was like, what did I get myself into? So if you have the option, it's either sulfate or sulfite. One of them has a lot of options. Okay, so something we can do to help us out is what might we do to one of these oxygens? Double bond it? Okay. Okay, so I'm going to erase this lone pair, and I'm going to make it a double bond. All right, so let's check if this oxygen is neutral now. Like, if it ends up being a -3, that's not helping us get anywhere, right? So oxygen, 2 bonds, 2 lone pairs. How many bonds? 2. How many loners? 4. So this oxygen is 6 minus 6, neutral. All right, so did we kind of just help our situation out a little bit? Yeah? What about our sulfur now? Let's see. With 5 bonds, right? 1, 2, 3, 4, 5. How many bonds? 5 plus 0. So what's our charge of our sulfur? +1. Okay, so sulfur still has a charge. So we eliminated one of the charges, right? We're still adding up to -2 though, right? Right? So this is another version of sulfur. We're getting closer to the best one. Again, best one is going to have the least charges. So what might we do to one more oxygen? Take what? The negative and do what?
Take away the positive and then make it a double bond.
Take away the lone pair and then make it